Most of you will now have heard the great news of the award in the New Year's Honours List to Mr. Bill Coates. This is for all his work for the Royal Institution, but most particularly, of course, for his masterly preparation of demonstrations in the Christmas lectures. Countless demonstrations, not quite since the lectures began 150 years ago, but for the last 23 years anyway. And I thought, therefore, before the lecture begins today, you would like to join me in congratulating and giving 3 rousing cheers to Mr. Bill Coates, MBE. Hip hip! Hooray! Hip hip! Hooray! Hip hip! Hooray!
Have you come to the wrong lecture? This is physics, and very important physics. It needs expert help, and Dr. Evans has come over here specially. He is one of the top experts in radiation safety, and he is going to offer to this tomato plant, which has been specially grown for you, a cocktail of radioactive water. The water contains radioactive phosphorus, and we want it's very strong. The cocktail is in the mug inside the greenhouse. So far, the plant has not drunk any, has it?
No, it's perfectly safe.
He's using a Geiger counter. We have to start with this because we have to give the plant time to drink. And we shall return to it at the end of the lecture and see how well it has enjoyed its cocktail. And so we're going to go straight ahead with Dr. Evans giving the tomato plant in a safe arrangement a drink of radioactive phosphorus. The little sounds you hear are small background counts of radioactivity which belong with the building. They belong with all London, for that matter. He's putting on a protective glove. It isn't too safe inside the greenhouse, so he's being very careful.
Pull the tray.
That's it. That's it. That's it. That's all right.
No, it won't. No, it'll have to come out. That tray will have to come out. That's it.
Take the tray out. Right.
Just put it in. That's it.
The growers are so enthusiastic, they grew us a larger plant than we bargained for. The smaller one, which was only 4 inches high, was tested out at Amersham Radioactive Supply Center. He's lowering the plant into the liquid, which is water, radioactive phosphorus, and some common phosphorus in phosphate neutral form, which we believe the tomato plant will drink. But you never know when you offer somebody a drink. Thank you. Dr. Evans will also watch everything else we do, since this is a matter of complete safety. In the last lecture, I showed you this tube with a little helium gas in it showing the beam of electrons in orbit. Electrons going round a round orbit, and I was so anxious you should see it well that I didn't explain what I have been waiting to tell you, why that experiment is so important. It was one of the experiments which started modern atomic physics, because by measuring the orbit, which you're going to see for a very short time, the room will be very dark for a moment or two, and you'll see up on screens the round orbit of the stream of electrons bent into a circle tethered by a magnetic field. It's not just pretty to see. We're ready to look at it whenever you say. We can measure the size of the orbit. There it is. Can you see a faint green circle? Can you see a faint greenish circle, a clearer one? It's growing smaller and clearer. Mr. Coates is increasing the magnetic field so that it whips it round, holds it in, tethered in orbit. Now you have seen again the magnetic field's effect on an electron stream. Now let's ask what it tells us. It lets us calculate from measurements of orbit size and of the voltage applied to the electron gun the relationship between electric charge on those electrons and their mass. We know something about their charge from other experiments, and we know that they have the same charge, except that the other one is plus, electrons minus, the same charge as a hydrogen atom, ion rather. An atom has lost its electron in electrolyzing water, in passing a current through water. And so the charge is the same. Now we can compare one electron with one hydrogen atom. And the answer is 2,000 times smaller mass. 1/2000th of a hydrogen atom. 1/200,000th of a uranium atom. A tiny chip of an atom. And so then, and this was just before this century started, then we were ready to make a model of an atom. It was a very crude early model going just by what you saw, which was that you could whip electrons out of atoms, and therefore they must, people thought, be inside. So here are electrons like currants in a bun or plums in a pudding. It was called a plum pudding or pudding model of an atom, and all the rest of it was positive sort of jelly all round like that. That's the early atom model. It was sufficient to remember and think about the way atoms did seem to behave. I'm going to turn from that today to radioactivity and again show you something that you saw before. I have the very, very delicate micro ammeter. A millionth of an amp will make the slave instrument, which is here, move quite a distance along the scale. There it is. There's the slave. Here's the main meter. And I'm going to bring to it, may I have an alpha particle source? I'm going to bring to it a source. But first of all, just watch how difficult it is if my hand comes near. That's nothing but my hand. The meter is so sensitive, it said, oh, your finger's got some electric charges because you're standing up above the floor or something of that kind. And so I'm going, it'll recover. I'm going to put here a small source. I'll have to put it so that it can talk to the, very delicately. See if it will talk. It says, yes, there's something making ions inside that cage. And the ions are being driven across by a 9-volt battery. They're being driven across the central peg. And when I take this away, the story will stop. There was something there. And it's something that makes ions. That's how radioactivity was discovered, that it can make the air around a radioactive material conduct electricity. There must be carriers that can carry an electric current. That's all I shall do with this. I shall disconnect my slave because he's rather inclined to follow every detail that happens. He thinks he's too important. I would like, therefore, to show you, before we proceed with radioactivity, 3 mystery experiments. These are mysteries. Don't try to understand them. Just watch what will happen and see how it goes. Before we talk about radioactivity, therefore, let us have the first mystery experiment. It's very simple. That's an electric light bulb. This is a supply line from a suitable voltage. This is a plate of copper. This is another plate of copper. Oh, nothing happened. Well, switch it on. Ah, the master switch. The lamp is running at lower voltage, but it still is a mains lamp. This is not an experiment you should try. It's thoroughly dangerous. I know there's an electric current going round this circuit through the copper switch, the copper wires, copper plates, and the tungsten metal filament. All through metal there is a current. How do I know? No magic, no ammeters. That's all a current is. I know there's a current there because we judge a current only by what it does, just as we judge a burglar, only by what he does. The spoons disappear. The current makes things hotter, makes magnetic fields, and can make chemical changes, as you saw in passing a current through water. Those are the main things an electric current does. You can't see it or smell it or hear it. You only judge it by its deeds. So I know there's a current there. It's not often I can say I know. A good scientist usually has to say I don't know. So we'll undo that because I've broken the roundabout circuit, and I will put back my glass jar and see if we can learn something new. You'll notice I'm doing it with one hand. I learned something new. Glass does not carry an electric current, nor does air. Try something else. Is this water? Yeah, water. Good, pure water. Nothing happens. So I complain to my chemist friends. I say, what can you suggest that is well equipped with carriers of electric currents, charged particles? They assure me that even in crystal form, salt is already in ions. The sodium atoms, here's that antique, out-of-date model, but it's useful for talking, with one orbit in the old view of the sodium atom so far out that it's very easy for a chlorine atom to swipe this extra electron and carry it to itself so that it becomes a negative carrier and the sodium atom is left positive. They're already there. Let's try putting in charged carriers from salt crystals, quite ordinary salt. Ready? That's not what you thought. That's not an experiment to illustrate electrolysis, passing electric currents through. You've seen that before. That's a salt counter. That's all it is. It counts handfuls of salt. I need the assistance of a young assistant who will pour out the salty water, fill it up with fresh, clean water, and every time I throw in a handful of salt, the lamp lights. You count the lamp, I throw the salt in, and you know how many times I've done it. That's the end of that experiment. The next mystery experiment is another one with something of the same kind. There was an electric field driving ions one way and the opposite charge the other way like that. There's an enormous electric field between these two metal balls. An appallingly big one. When Mr. Coates, where have he got to?
About about 15,000.
15,000 volts between one ball and the other. I'm rather keeping away from them. And there's a large storage capacitor to store up charge in case either of the balls needs extra charge at each of the two signs. Now, Mr. Coates is going to do something very surprising. Just watch. Wake up your neighbor. Tell him he's going to do it again. So, oh, sorry. Ah, yes, Mr. Coates, counsel's caution. Then it's all right. A third one, very much similar, is going to be only 4,000 volts this time, between a little grid of wires, vertical wires like my fingers, with a few millimeters behind a plate, a round plate, about the size of a 5p piece. And I want an alpha source, please. I've got it there. I'm going to bring up a small creature here, and I better tell you already what it is because you've seen it used. It's a radioactive sample which shoots out small bullets called alpha particles. There's no mystery about alpha. It's the first half of the word alphabet, and it's the first letter of the Greek alphabet. I'm going to turn on 4,000 volts between these wires and the plate. An enormous electric field. The camel's back is ready to break. Remember, that was what happened with the spark that you saw just now. The camel's back broke when a cloud of ions from the flame started up a cascade like that cascade of marbles you saw at the earlier lecture. This is a spark, an avalanche of electrons barging more electrons off, atom after atom, molecule after molecule, as they go crashing through, driven by a huge electric field. It is an avalanche. So it will be here. Watch carefully. Can you see the sparks? Can you? Up at the back. You are seeing each spark the sign of a single radioactive atom exploding and hurling out a tiny chip of its nucleus and making a spark by the ions that makes as it blunders through the air. Can you hear them? You can see them up on monitors as well. Now this too is a counter. We had a match counter, we had a salt counter, and this is what kind of a counter? What's the word? Alpha's all right, it's rather sophisticated. What kind of a counter? What's the common name of a person? The person who invented it. Geiger counter. This is the simple open-air Geiger counter. Geiger counter for showing that you've got electric charges. This? What? We'll try a piece of paper to see whether alpha particles will go through paper. We'll hold the paper up. Unless there's a pinhole, nothing happens. Take the paper out. You can't go through ordinary paper. I wouldn't like to open up a cigarette. It might shock somebody, but I can assure you if we used cigarette paper, the alpha particles could just get through. Not pinholes, but thin paper. It's about their limit. 2 inches of air, cigarette paper of paper, and nothing thicker. So they've got a very short range, and they do a frightful amount of damage as they go. 100,000 pairs of ions in air. And you'll even see a photograph of that presently. From that, I would like to expand the story about Geiger counters by drawing how these things are arranged. The earliest one was just a very, very sharp point, and a very sharp point with a little cage round it, and you had a big voltage like that, and you brought the radioactive material near, and it shot these strange alpha particles through, making ions everywhere. That's an old-fashioned one. I don't cross out all old-fashioned people. Grandmother is still safe, but I am going to show you the more modern form. Instead of a wire, instead of a grid of wires, a very thin wire. This is very thin, and it's surrounded by a metal cylinder, like that. The wire is to have a very intense electric field round it. Here is the electric field straight out from the wire to the rest of the metal tube round it, and there's a very, very strong electric field just near the wire. It's like that point that drove smoke that you saw in an earlier lecture. And we get that strong electric field by connecting the wire to about 4,000 volts, plus, minus 4,000 volts, and then round to the outer case. If you can shoot through that space, either because it's strong enough to get through the thin walls or because it goes in through a specially thin window, we'll change this and call it a thin window here. There's a thin window, thin, like my green pen. There, if we shoot in alpha particles, we will find as they go in, they make ions. Now I have to make both plus and minus ions at the same time. The ions, which are electrons first, torn off, air atoms, are driven towards the wire. The wire collects them up and sends them round in a great hump round the circuit, a sudden pulse of electric current. You can therefore put in here some form of ammeter. We had our little micro ammeter doing that, but better still, we can amplify that pulse, and then we have a Geiger counter. The Geiger part of it is just the sharp, thin wire. The counter part of it is a machine which you will presently see, but first you should hear it, because we can send the pulse through a loudspeaker. Here is the pulse going to go through a loudspeaker here. We will make a gap. Oh, some things defeat us. We'll make a gap here and connect it to a loudspeaker like that, and then out will come the popping noise that you associate with Geiger counters. I have a Geiger counter tube, a modern tube here for you, and we've seen what an alpha source does. Why alpha? Because there are three different kinds, so different we have to call them Archibald, Bertram and Gertrude, only we use the Greek names instead, just for fun. Here is a beta supply. Here at the end, a little metal thing at the end that I'm putting my finger a little dangerously near. All right? Well, he says all right. I'm going to bring that up close here. Now let's see if it'll go through a telephone book. Very little at that distance. Half a telephone book. These creatures can get through half a telephone book, quicker than you can read it. Quarter of a telephone book. A few get lost. So much for the more penetrating creatures, which actually are very speedy electrons. All they are, they're very fast electrons which can stagger through even a quarter of a telephone book, and each pop there shows one of them arriving, one nuclear explosion that spat out something, and what it spits out is a very tiny part of the nucleus. Mr. Coates, you're offering me your watch.
Yes, it's my old army watch, actually.
His old army watch. Bring it along, try it here. Do you wear it?
Yes, I wore it for about 10 years.
Dr. Evans, is it safe?
Well, I wouldn't like to wear it the wrong way round, but he wouldn't do that anyway because you
show
couldn't
it.
read it.
Now that's at the back of the watch, which is heavier and metal. Now comes the front again. If he wore the front strapped onto his wrist for 100 years, would it be all right?
I wouldn't like to do that, no.
It'll be hard to tell time.
I would like to try now, if I may, the third kind of source. Dr. Evans, have you got a gamma ray source here?
Yes.
Alphas are great big blundering helium nuclei. They're helium atoms without their electrons, and that we know from other experiments. Betas are high-speed electrons. There is his counting tube there, or gamma rays, it doesn't matter where the tube points, because they're so penetrating. He's coming in from over there, from out of the door. He's going to bring in a strong gamma ray source. Even this one's talking as well. Doesn't make any difference. Okay. Good. Thank you. Please take it safely away. You know, for a small source that's compact, almost an inverse square law operates. So when he's twice as far away, he's 4 times as safe. And if he's 10 times as far away, he's 100 times as safe. The best thing if you fear gamma rays is to run away. I'm going to show you another way of looking at radioactive things that come out. But before that, I would like to show you that the beta particles are electrons. They can be bent into an orbit. Mr. Coates has brought in a source there and a counter. It isn't very noisy. Oh, he's got something there. There's a lead sheet getting in the way. Take the lead sheet out. Ah, that's better. Wait a minute. Out. There's the source. There's the counter. And put the lead sheet in, and it protects the counter from the source pretty well. What little you hear is just strays from the room in general. Now move in a magnet, so like my finger, the electron stream can curl round the lead sheet. They go up through that space, curl up and over into the counter. Move away, doesn't work. Mr. Coates, are you able to reverse the magnet?
Yes, we can do that.
You can. He's going to try the magnet the other way round. Get something, strays, but nothing very impressive. Now turn it back the first way. That can tell us that the beta particles are negatively charged, can be bent into an orbit skirting round the lead. We are going to next look at another form of counter, a counter which is quiet and shows numbers to you and will be much better. But we're going to bring that in. Meanwhile, I'm going to talk to you about what we know about these different kinds of particles. We'll get ready, therefore, for 2 experiments together. First this one, and then the picture we'll draw of the different particles. This is called a readout. You will see big numbers here. Good heavens, it's already talking by mistake. You be quiet. It reads 888 the way your hand computers do, and now we'll tell it to be quiet like that. In fact, we can switch it off for a moment. We'll bring here, please. Oh. Well, I haven't succeeded in switching it off, have I? I think now I have. You be quiet. I need a source, please. Now we'll switch on. Can you see? I can stop at any point. I can tell it to stop now, and it reads 404. And it'll stay there until I tell it that it can go on counting, and it'll count right up into thousands. And if I want to, At any time, I can tell it to go back and start again like that. That is my large figure readout, which you will meet again quite soon. I want now to show you a picture which just sums up what we've talked about so far. In this picture, I have 3 little radioactive supplies, each in a lead tunnel. We call it a gun, but it doesn't shoot like a gun. Out come from the radioactive supplies these tiny chips, which we soon find are only parts of a nucleus. Alphas go an inch or 2 in air, most of them straight ahead. Betas go wander, 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 wander for a foot or more. Gammas go zippity, 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 zippity with the speed of light, straight through. If they go through you, they don't hurt, do no damage. If one stops, it might whip out an electron and make some cell a little sore. Gammas can be stopped by thick bits of lead. Alphas can be stopped by only thin paper or gold leaf. Betas can be stopped by thin layers of aluminium. And down in a vacuum, all of them will travel through a vacuum, and all of them will make heat if they're stopped. And for down here, again in a vacuum, alphas show positive charge, betas negative charge, gammas no charge, and they go right through the whole apparatus. I would like to see what happens when a radioactive material does throw out something. After its nucleus has thrown a particle out, it's different. And so it's a different chemical element. And we will show you that happening. It's called radioactive decay. And we'll show you that it happens by our model. We'll imitate what really happens. We will show you that it has a half-life. After a certain time, half the atoms have blown up. After an equal amount more time, half the remainder have blown up. So you start with a big supply down to a half of a half of a half of a half of a half. We're going to illustrate that with those members of the audience who have got a plastic glass. Come down and receive a coin. The instructions for the glass holders are going to be, over 30 of you, so you'll have to form close lines all round. Don't tread on the apparatus. And you're going to have in your glass here a coin. And the coin is going to be on one side black, and on the other side white. There's a black mark there, and on the other side of the coin, it's a white mark. So that the people who have a white mark will, when they reach a white mark, will have to go back to their seat. The people who have a black mark will stay in. Now, I'm going round to be a sort of master of ceremonies, and as soon as everybody's got a coin, is anybody who's not got a coin? I'm going to sit on the seat here and administer the treatment. You will have, I need a clock, Mr. Coates, please. You will have 10 seconds in which to shake, don't do it yet, please. Shake the jar up and down with your hand over the top. Close the top, please. Has everybody got a coin? Then in that case, you'll have 10 seconds in which to shake it. At the end of that, I shall say stop, and when I stop, you look in, and if you've got a white blob on the coin at the bottom, you go home. You've decayed. You've blown up radioactively. If you've got a black one, you stay here. Now you watch what happens. 5, 4, 3, 2, 1, stop. 5, 6, 7, 8, 9, stop! Don't change anything. Look, If you have a white one, come back to your seat, please. That's one half-life has gone. And if you look, go on back, you'll find about half of them have gone. Are you ready? Steady, go! Ready, stop! Watch it, don't change anything. White ones, go. It's another half-life. Look what's happened. It happens quickly. This is called exponential decay. It's how radioactive atoms change. Ready, steady, go! Ready, stop! Have a look. White ones go out. You didn't think it would happen so fast, did you? Nor did they. Ready, steady, go! Ready, stop! White ones go out. You can join up. Ready, steady, go! Ready, stop! White ones go out. Well, it's got down to a pretty difficult business by now. We're down to individual atoms so that statistics of great populations don't apply. And it's a question of how long the remainder will last, but you want to see it. Ready, steady, go! Ready, stop! Whites go out. Ready, steady, go! White, ready, stop! White go out. Well, it's down to individual question now. Ready, steady, go! Stop! Whites go out. Wait, what's going on here?
It's got two brands.
Oh.
Two brands.
Oh. Oh. Two non-radioactive stable atoms, the other isotope, got in, and they'd have stayed in forever. Thank you. Now, wait a minute. I'll give you the present. You want to move on. The next illustration of the meaning of half-life I want to give you is with this rather beautiful diagram we've got. This great big green field, blue-green field, represents atoms, a population of all one element. Atoms are the same chemical element, which is radioactive, all of them, with a constant half-life. And now we're going to take, at the end of a half-life, I shall say 1, 2, 3, change. And that represents all the changes, well, I count. 1, 2, 3, change. And all those disappear into a different element, different chemistry. 1, 2, 3, half of what's left, change. And 1, 2, 3, half of what's left, change. And 1, 2, 3, half of what's left, change. And 1, 2, 3, half of what is left, change. We're getting to half of a half of a half of a half, and 1, 2, 3, half of what's left, change. We'll stop at that point. That's all I'm left after all those half-lives, and that's all I've gained of the other element with a different chemistry. Thank you very much, and thanks to the expert who made that diagram for us. I'll give you one more illustration of half-life. Why do I bother? Because it's extremely important. It's the way radioactive materials or fission products, which are radioactive, decay away. If you have a very short half-life and you keep it near you, it will have finished decaying away and shooting things out in a very short time. And so the thing to do with radioactive materials with a short half-life is to keep them in the attic for a week or two. The phosphorus that we have here with the tomato plant has a 14-day, 2-week half-life. So at the end of a month, 3/4 have gone. It's only a quarter as much active stuff as there was. At the end of a year, how many fortnights are there in a year? How many fortnights in a year? 24 fortnights in a year, or 26, whichever you like. Well, if you go down a half of a half of a half of a half 24 times, you've got very little left indeed. If it's a long half-life, it doesn't decay very fast. If it's a small supply of radioactive material, you could keep it near you without any fear of damage. But if you kept it near you for several hundred years, of course, that might be a different matter. I'm going to show you very quickly with my calculator just another illustration. I'll turn on my pocket calculator. I will tell it that we are going to deal with half-lives. So I'm going to divide progressively by 2. And I'm going to start with 1,000,000 atoms, a bit more than 1,000,000 for a nice round number. So 1, 0, 4, 8, 5, 7, 6. It's a convenient number, a bit over 1,000,000. And I'm going to press the button every 2 seconds. 1 second, 2 seconds. Oh, I did it twice. I beg your pardon. I pressed it twice by mistake, so we've gone down from 1,000,000 to 1/4 Press it again, still less. The last figures change about quite a lot, of course, because from one trial to another you get statistical changes. I'm going to try again. 131,000, 65,000. Half again, 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 half, 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 half. Well, now it's getting awkward. 2, the last atom. The poor calculator, of course, doesn't know. So the wretched creature goes on outside real nature, and the next one will say what? 0.5. And the next one, stupider still. We can't chop up a nucleus like that. Not normally, anyway. I have here a very brief look at a family tree, one of the radioactive materials. Here's the family tree with the half-lives shown. Just look at uranium with a half-life of 4,500 million years before it drops to a half. And then other ones here, the daughter of uranium, 24 days. The granddaughter, protactinium, 1 and a bit minutes, just over 1 minute. And still further down, you will see polonium, a particular one, with 0.00016 second half-life. An enormous range, and chemical changes in the sense that each time the atom explodes, if it is in a series like that, it's a new element. And so I would like to show you from that a very special exhibit of 2 traveling decay curves. This is an animated exhibit which has been made specially for you. I don't know where it goes. How would you like this? As it is, all right. I'm going to illuminate this curve, which is the stockpile decaying. And here's the number of atoms left. This is the second one. I want to illuminate the first one first, please. I'm going to show you how the stockpile decays as time goes on, half and half and half and half and half and half, like that. We thought it so beautiful that we got it ready for you specially. This one is the number of atoms left goes down, 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 like that. Somewhat the same story. Thank you. Good. We're going now, and you must be tired of seeing models, to measure the decay of a real radioactive element. We have, as you heard just now, a granddaughter of uranium with a very short half-life, and we're going to measure how it decays away. We're going to do some chemistry here. We have a solution of uranium, which I'm shaking up. It has above it an organic solvent, a special liquid, which picks up the granddaughter only, a little uranium, but none of the daughter, and pretty well all the granddaughter. And when we put it here on a suitable block, thank you, we'll let it settle down until the counter looks at the top layer where the granddaughter is, and we'll see what we can count. Of course, it's already talking in a most outrageous way. I need the clock, please. Thank you. I am going to count. Every half minute, take a count, and I'm going to start with the counter switched off. Now then, I'm going to start from 15 seconds, go. And I'm going to count for 10 seconds. 25. Stop. 338. Please record that. We go out. I started at 15 to 25, and I will start again at 45 seconds to 55. Ready, 2, 1, go. Half a minute later than it was. And now I'll switch it off at the end of a 10-second counting trial period. 266. I'll wait now until 15 seconds is up. This is a real radioactive experiment. On. Okay. 212. I'll start again at 45 seconds. I'm timing every half minute, and I'm taking a 10-second run each time. We have to allow for the general radiation in this room, and for that I shall take a previous answer. We have worked it out by trying it. Stop it. And we have 163. And the average rate is 10 or 11 counts in a 10-second period. So I'm going to ask my recorder to take 10 off each measurement like that. There's a measurement coming now. Stop. 137. The last one will come now. Go. Notice it's got a short half-life. You can tell it has by what you see. Stop. 90. Give me those, please, and I will plot them on a rapid graph. You can't find it? All right. That's all right. We'll draw a graph here very quickly. Here we are. We will draw an axis along like that, an axis up like that. How many minutes, how many readings have we got? All right. 1, 2, 3, 4. That's enough. And we go up to, what do we start? 328, all right? 1, 2, 3. 328, all right? This is the count. This is the time. And this is O, 1 minute, 2 minutes, 3 minutes, like that. So first of all, the count is 3:28, you say? 3:28, just about there, right? Next one, yes? 2:56 at the half point there. 2:56 is about there. Next one? 2:02. Next one? 1:53. Next one? 1:27. Next one? 80? 80? Well. Yes, next one? That's it. All right. Now we take that and draw a nice curve down through it like that. Oh, well, this is an experiment of principle, and I want to see what it's like. And as long as you can see what it's like, that's all we need for the moment. We start here. We'll start at just 1, 2, 3. Where did you go through? We'll have to put in a different color, please, here. There's 1, 2, 3 for a marking point. Now at 1.5, take 1.5 across to there. There it was. So you go from there to there. How much is that? That's 2/3 of a minute and another 2/3, 1 1/3 minutes. And if we start at another place, let's start there and go down to half there, and we go down to there, and so it's from there to there, about 1 1/3 minutes. So it's 1 1/3, 1 1/3, and you find it goes on like that, and the time is, if you want the professional measurements, 1.2 minutes instead of 1.33. There you have radioactive decay measured for you. The next radioactive measurement or instrument is a very important one, which we call a cloud chamber. Mr. Coates, would you please make the cloud form in that big bottle? You may need to look at it both in full light and part light. We'll see. We're going to compress the air in the bottle. It'll heat up. We wait till it's cool, then we let it expand. Watch it.
Keep going.
Can you see the cloud? Watch it again. Somebody give me some matches. No, it doesn't matter. Mr. Coates, got any matches?
Yes, sir.
All right. Let me throw in matches and see if the ions from the flame help the cloud to form. The cloud drops of water form on salt particles, ions, anything else as a nucleus. And we have here a radioactive source which we hope is making ions along thin tracks of the particles, and we want you to see them. You may be able to see the tracks. It's difficult. Watch carefully. This is an interesting experiment, but a difficult one. Can you see the little tiny tracks, white lines of drops going across the box? Go. There. Each of those is the track of a single alpha particle and is very important. I'd like you to see now some photographs of such tracks. There is a photograph of tracks of alpha particles from a radioactive source out at the left, there, out at this side, and they're straight. That's the evidence that atoms are hollow. That was the thing that finally convinced some doubters about the existence of atoms. When they were doubting, they were sure that these tracks showed individual atoms. I would like to go from that to the rare case when there was a violent collision. That told people there are nuclei, massive centers to atoms. Next, there is a row of cloud track pictures of atoms from radioactive source here in hydrogen, flipping up the hydrogen core up in this direction to my finger, while the poor old alpha particles staggered along. Now look at beta particles, which you will see are very, very wild little stagger things like that. And that is the way they behave, because they're only light electrons, very easily deflected from their path. They're like your younger brother. The gamma rays which went through here hurled out electrons and made that mark there. And now look. This is a very strange picture. There are two paths here. There's an unknown source over there, one side, and it did nothing until something reached invisibly an anvil of some nucleus there and hammered out two particles, one bent that way, the other bent that way, bent by magnetic fields. So one is positive, one is negative. This is a positive electron and a negative electron born from nothing but a flash of light. This is a photograph of the creation of matter. We shall show you some more properties of light and things that we'll do at next lecture. And it is time to ask Dr. Evans to look after the health of the tomato plant. Listen over there.
Shall we take a top leaf off first?
Take a top leaf off first. By the way, nobody must leave the room until the last remains of radioactive material have been taken away by Dr. Evans. That's a general precaution of safety. He's bringing a top leaf high up on the tomato plant. This is a tracer to find what happens. It drank. It did. Take a bottom leaf and see if it drank more to the bottom leaf. This is absolutely genuine. There's no fake. It would be easy to fake, and we wouldn't do it.
I haven't got very many good bottom ones.
Quite well, any respectable looking bottom.
That's a reasonable one there. Let's hope that that one will work.
I'm very grateful to the Amersham Radioactive Supply Centre for providing the phosphorus. It's had to come here by special messenger.
I think that's the one. Let's try it. Looks a bit sorry, but it may have worked. No.
No, the sorry leaf didn't drink. Do you want to try one of the healthy leaves?
Try a good one.
Somewhere about here.
Right. There's a nice little one there.
Right. When you've seen this, you have seen radioactive tracers put to use to measure growth in plants, to measure your bloodstream carrying salt in a drink, radioactive salt down to your big toe, to see the measurement of a thickness of a steel sheet. That did quite well.
It's rather more because it's a smaller leaf than
Rather
that
more,
one.
and because it's nearer the source of supply. You have seen real radioactivity put to use. Thank you. That's all.